interesting stuff there for people who have a problem. Okay, just kidding. I'm going to close this a little quick, otherwise I need to close. All right. So I have posted some lecture notes. You do. All right. Feels nice. Feels nice to be able to talk to people. No, it's much nicer than just.
It's less crowded than last time.
Yeah, well, we are almost to capacity now. No, we have a few more places available.
Maybe people have embraced the idea of doing that which is far away.
That's a good one. Yeah, everybody wants to do large scale geometry for far away. So, yeah. I have to say, I've been so nervous. I couldn't think about anything but this camera for last day or so. And I met someone on the street, another colleague of mine, and he says, "How are you doing?" And so I'm worrying about the camera. So, anyhow, so shall we start? Start with the map. Okay, so any questions from last time? Anything that we said? Comments? Something here? Not here? So typically, if you don't remember anything being unclear in the next lecture, that's a good. That means either you've understood everything or it doesn't matter. In either case, right? So last time we started to say that large scale geometry is something that we roughly said all things up to bounded, finite, compact distortion we don't care about, right? And our example, the only example that we worked on, we said that this is a large scale equivalence. These two things look very same when you see them from far away. This is the example. So the whole lecture today is to basically formalize it. We'll formalize what this means, what it means to be large scale equivalent, and in fact generalize this. What did Rothennig said? He said, be wise, generalize. So we will generalize this piece of information. But first we need to say what is a large scale equivalence. So right now we are thinking only in terms of metric spaces. So let's just continue to think in terms of metric spaces, and let's just focus on saying what is large scale equivalence for metric spaces. What is large scale equivalence for metric spaces? So what does metric space have? What is the only thing that a metric space has? It has a function b given to us. And where is this function defined on? This is defined on the product space. To our, I don't know, what do you say that? Not plus, I also need 0, right? Whatever. 0 infinity is how I should have written it, but sometimes one forgets to write things properly. So, this is the only information we have on a metric space. We don't have any other information on a metric space. But what you notice is that this set has some interesting structure to it. And we are going to use this structure not so much this time, but we want to make ourselves cognizant of what the structure is. So what can you do on x cross x on any set x? So operations. So there is a jargon for it which we will not use. It's called a pair groupoid. For people who care, this is the jargon for it, but we are not going to use the groupoid lingo and structure anyhow for the course, but just so we know. So one thing is that if you have such an element, there is also an element. What should we call that guy? So one should think of xy as an arrow from say y to x. Right? So we consider this an arrow from here to here, or a function from y to x. So what will that be? That will be the inverse function, the inverse arrow going from x to y. So this is one operation. The operation of inversion is there on any pair groupoid or any groupoid. The second operation is it's only possible when you take two arrows that can be composed. So this is an arrow that starts at z and comes to y, and this is an arrow that starts at y and comes to x. So if you come to the same place, if the range of this is equal to the domain of the next arrow, then you can compose them and call it. Yeah. So these are two operations on the set x cross x, and our metric is a function on x cross x. So maybe we should think of defining something using the metric, something that works well relative to these operations. But this is not so important for our situation in this case. So, okay, I mean, before I've already gotten into technical nitty-gritties, but before I started with the technical nitty-gritties, I wanted to say a few words about the plan for the day. The plan for the day is, of course, a theorem which generalizes the fact that this is an equivalence. So by the end of today, we should know, and if somebody could tell me how to pronounce this name. So this is our plan for the day, the Svarc-Milnor theorem. I don't know how to correctly pronounce the name Svarc, but my pronunciation will have to do. In absence of anybody who knows this kind of name?
Probably it should be Schwab.
Schwab.
The head on the S is a sh.
It might even be Schwarz then.
Might even be Schwarz.
It might be a different way to write Schwarz.
Schwarz.
Possibly, but
okay, good. Because I think the only place I have heard about this is in US, and whatever you hear now, actually I can still not, after living, and I speak quite fluent German now, but I cannot pronounce German mathematicians' names correctly because I did my PhD in the US. Right? I got so brain damage. I have never recovered from the inability to pronounce the German names correctly from there. So, okay, so Schwarz is what we say. Okay, so that's the theorem we are going for today. But we should first define what large-scale equivalence means. Whatever. So I'm taking it slow, and the proof of all these things in some detail are available in the notes that I've uploaded, and so maybe it's possible that in the run of the class I'm not going to give you all the details, but if you have questions from the notes or whatever, you can ask me later. Okay, so we have a distance function. So what we can do is for every r greater than 0, we can define. So for people far away, large scale people, can you read what I write? Maybe you can. Somebody should just clap.
I think we can't hear them.
We can't hear them. I thought this was also a possibility, right? That they could ask questions.
They can ask questions in the chat. Can you?
Shall I turn it around? That is much better. If I turn it around, then you can all have fun. Because I anyhow don't see anything. So
there is no question. And nobody is.
Huh? It's on there? Okay. Okay. Anyway, so entertainment is also available in this class. So let me go down and go back to what I was saying. So for every real number bigger than 0, we can define a set which average is called ER or ER for the set space X. This is all xy such that the distance is less than r. Right? So this is the set of points that are r close to each other. Okay, and such sets are called, these sets are called scale or controlled sets. So if you want to define an equivalence or large-scale equivalence of metric spaces, one thing that should happen, what should happen? You are all mathematicians. If I define some set like that, and I say I want to have some property that will preserve a large scale, what should happen? It should make sure that the image of such a set is contained in another such set. So this is a property that I'm going to define next. Or shall I wait a bit? I don't know whether it can be visible from down. So a map which is not necessarily continuous, right? Not so there is a map f x to y of metric spaces. It's called Bono-Logos. I don't even know how to spell it correctly. By the way, another side effect of being blind is that you never learn to spell because you never read correctly. You just guess what it is written. So logos if for every r f of e r x is contained in E some S y. There exists such an S. Right? So for every R, there should be an S. Such that. So let me write it in plain simple English. For every R, there exists an S greater than 0 such that bxy less than r implies bfx fy is less than s. Okay, so this is kind of different from being continuous. It is saying that things that are short distance from each other are going short distance each other. How do you define continuity? You define the other way. Inverse images of open sets are inverse. Right? So this is the first mistake that some people make when they when they are taught continuity in a calculus class, and your teacher beats you up, don't do this. But we are going to do this. Okay? Because that's what mathematics is about. Anybody tells you not to define something, define it. And give it an ugly name. Bornologus. So there is another thing that is important. So this is one thing that is important. And I'm going to elaborate this property a little bit more. But the second thing that's important is kind of obvious if you want to preserve large scale geometry, is that you don't want the infinity, something bounded in the other set to come back and become infinite in your set. Right? So inverse images of bounded sets are bounded. Right? You don't want something that was finite somewhere become infinite in your world. So this property is sometimes called proper or metrically proper. Right? So this is not so difficult. These are the two properties. These are all the two. This is the only two set of properties that we care about, and that's all. If we have 1 and 2 in a map, we call that map as a large scale map. Okay? So definition, a coarse map f from x to y is homologous and proper. So this is what it means to be a large scale or coarse map. So I'm just for once giving the definition without having to think too much about it. And since we are only going to use these two blackboards, I will have to become more efficient using that. Oh, this is funny. The last time I think I started the discussion about length spaces and geodesic spaces, but we never really finished that discussion, although it was contained in the notes. So let me say that this particular property, the property of sending these controlled sets to control sets, or making sure the distances are well behaved, it becomes much nicer in a length space. So what was the length space again? You guys remember? So a length space so this is really, I don't think the people out there will be able to read it from far away. It's so much.
I mean, there's no one.
Huh?
Right now there's no one, but I think it's readable.
Yeah. Well,
That's okay.
all this work, for technology, and we have to stress Tobias for it, and then nobody watches it. That's okay.
Well, maybe they'll watch the recording as well.
Yeah. Maybe it is just not streaming. Sometimes I've also heard stories that the video is going, but you think it's going locally, but it's not being transmitted far away. So a length space is what? Do you remember what a length space is? So length space is something that has lots of curves. That's how you should think about it, right? So a length space is a metric space xd such that for every xy in x, the distance xy is the infimum of length of curves. Gamma 0 is x, gamma 1 is y. Okay, so it's not necessary to define it exactly this way, but the infimum of all curves should be equal to the distance. Infimum of, so you should have sufficiently many things in your length space. So if you make this assumption, this is an infimum assumption. It does not guarantee that there is a shortest path between 2 points. It just says there is an approximation to the shortest path, if there was to be one. So there was a second concept that we also defined last time, which I will just quickly remind you. Geodesic space is, there is a gamma such that L gamma is dx, xy being endpoints of gamma. So there is a gamma. So this is for any x comma y in x. It's for, this looks like a ridiculously complicated definition, right? It looks like, how on earth are you ever going to check? Are you going to sit down and look at every pair of points and see if there is a path and do this calculation for every curve and see you can actually go from here to there in exactly that much time? And there is such a path. How are you going to ascertain that something is geodesic space? So one thing we said last time was that every complete metric space, every complete Riemannian manifold, the metric is geodesic, and that was called the Hopf-Riemann theorem in Riemannian geometry. So I'm going to say there is a Hopf-Riemann theorem for metric spaces, and that says precisely, and I'm not going to prove it though, so I'll just state it though, but I need to define a concept for that, which is, I did not do it last time as well. So XD is a proper metric space if what? Does anyone know?
I think if D is a proper map.
If D is a proper map, what does that mean?
Closed balls, small closed balls are compact.
Yeah, so basically all closed and bounded sets are compact. Closed and bounded sets have to be compact. This is just the definition of properness, and the Hopf-Riemann theorem says proper is good. Okay, that's all you have to remember. This property is important. This property is important because this property is interesting. The only reason this property is important, the property of being proper is important, because property of being geodesic space is interesting. Obviously, right? If you can find curves with some property, then that's something. So I think today the camera is running, but somehow it has stressed me enough to slow my brain down to almost what you call asymptotically flat. I think having one more blackboard is really useful. So if nobody is actually watching, if you're sure nobody is watching, I might as well write there, right? Because you guys can read what I write there. It's a little bit of cheating though.
Is someone there?
Right now, no.
Is it being recorded? That's maybe alright.
It's being recorded, so maybe it's.
Okay.
I mean,
But you can
you could also just turn the camera.
Is it easy to turn?
I don't know.
Okay, yeah, but.
But you can do that. Okay, yeah, bad idea.
I think I'm just over here. Where did I will check a new chart because I will not probably find the old one. Okay, so we'll just stick to this one you said? Okay. Okay, so where was I? See, this is what happens. As you grow older, you don't remember where you were standing.
How things become easier in length space?
Yeah, so we have we have defined a proper metric space, and the theorem, which I will not prove, is that locally compact, complete length space is proper. Are you thinking, yeah, you're just juggling around some words which you are not interested in? Okay. Otherwise, a proper length space is complete and locally compact. That's complete area, right? This again the converse, but what's the deal? Any such space is a geodesic space. Okay, so if you have what looks like a very natural condition, properness, local length space, then you are automatically guaranteed completeness, local compactness, and geodesicness. So these two things are easy to verify. Oh, is my phone telling me something, but let's ignore it. Properness is easy to verify. Being a length space is not that hard to verify. Implies completeness, local compactness, and geodesic space. Awesome, right? So this is Gromov's version of Svarc-Milnor theorem. The proof is actually interesting, but not difficult. It's really an interesting proof, but I'm going to ignore it. I have to say, one has to advertise some proofs sometimes. No? I mean, I would very much advertise that proof without giving it to you. It's worth knowing. Okay. So all this was about just preparing all kinds of objects that we might be interested in. So this, we have now defined, is it still our definition still here? No, it's gone. The notion of large scale maps. And one of the things we defined was this Borologos map. So here is a lemma which works if you assume length spaces. Why does it work if you assume length spaces? Is pretty much obvious as soon as I write it, right? So if XD is a length space, a map f from x to y is a monologus, which means that for every r greater than 0, there exists an s greater than 0 such that when the distance of x, basically you are taking these control sets in x, taking their image, and they should be inside some control sets in y. So its monologus is equivalent to B, f is large scale I've spelled Lipschitz correctly? Hopefully.
Yes.
As I said, I don't spell correctly, but more or less people can read. Thanks to the things, editors, it's not so difficult on a computer to spell correctly. So what does it mean to be large scale Lipschitz? This means that there exists constants c greater than 0 and a greater than 0 such that distance of x or fx fy is less than equal to c times distance xy. If I just wrote this much, if I wrote just this much, is everyone familiar with this? What does this define? What does this tell us? That f is Lipschitz. And up to a bounded error, this is what's called a large scale Lipschitz map. Right? So these two things are one and the same thing. Okay? And another thing is that in this definition you used every possible R and every possible S. What is sufficient is there is some R greater than 0 such that there exists S greater than 0 with the same thing. If dxy is less than R implies dfx fy is less than S. So if it is only true for one R, then and your space, the domain is a length space, then it's true for all S, for all R's. Why would that be? So I don't want to write a proof, but I want to draw a picture. Just one picture to show that, of course. And that helps us also think why is such a definition so powerful? Why is the definition of a length space such a powerful definition? So in mathematics, there are two kinds of definitions. There are definitions that one wants, like a definition that is the definition of the God, definition of the cake you want to eat, right? But then there is a definition that is useful, and this is a useful definition. It helps you bake the cake you want to eat. By the way, how many of you are actually master students? I know one. So?
About half of us.
Oh, good. I was actually being unfair to you guys then. Because I was thinking everybody here is a PhD student. And I might have been going a little too fast. It's good that I asked this question now, before I make the mistake of assuming, of course you know this. I'm not going to do that anymore. Right, so I'm just getting too slow. So I want to give only a picture to prove the lemma that I have written there, which says some property of large scale maps. And that picture is the following. So if I have a length space X, and I want points which are far away, right? So I can join them with a curve which is close to the distance. And on this, I could travel distance r, then to next point in distance r again. So this is x, this is y, and I can make x1, x2 till I get there, right? And in y, I look at just the images of these points. So this is f of x, f of x1, f of x2, so on. So what I know, if I am only going a distance r, this will be within distance s. This was r, this is going to be distance s. I don't know if there is a curve here, but I know that the distance will be less than s. And similarly, I know the distance here will be less than s. And so on. So it tells me that if I make r's bigger, I can also choose s appropriately to make my formula work for all values of r's and all possible values of r's. Right? This is the proof of the lemma. The smaller values of r's are no problem here, unlike in topology where you have to always think about epsilon goes to 0. So if I assume something works for there exists an r for which there is an s, for the smaller values of r, the same s is good enough. Right? The same s still exists. So this is why this is large scale geometry, because in these concepts, you're worrying about r being big. You're not worrying about r being small. So you have to find s when r is big, not when r is small.
So the moral is somehow in geodesic spaces we can find nice subdivisions of the total distance and work with that.
Yeah, so I mean, you don't even need geodesic spaces. You need just the length space where you have approximately a geodesic. That's good enough. And when you have geodesics, then a lot more magic happens, of course, which we'll talk about. Okay? So, any questions so far? Okay. So now I'm going to change gear. So this course contains metric spaces, and it certainly contains groups. So usually there are people who get indoctrinated in mathematics to be allergic to one or the other. Right? There are people who do geometry say, I don't want to think about groups. And there are people who want to do group theory, say, I don't want to think about analysis. I would put another point where I had said complete Riemannian metric is Hopf-Renouf theorem. There is an analysis that corresponds to it, which we will not talk about in this course. On a complete Riemannian manifold, the Laplace operator is self-adjoint, and you can do all kinds of nice analysis with the Laplace operator, only on a complete Riemannian manifold. And therefore, the heat equation knows about your geodesics and blah and blah and blah. So there is a whole connection. You should not think of mathematics as dueling kingdoms of groups and geometers and analysts. Although I have to say, analysts are grumpy. Right? And I do analysis in winter. Just kidding. Group actions. So we'll change gear a little bit and we'll talk about group actions. So actually, in the example, and I'm going to write here, because this is not important. This is not important for people far away. I want to remind you of two concepts. One is of fundamental group and of group action, whichever. So if you look at a circle, right, and you have the R. This is the fundamental group, the covering space of the circle. This is covering space of the circle. And what's the fundamental group? It is that. And this group acts on this space by translation. Right? So you can take x goes to x plus m. So, which is the action of n dot x equals x plus m. So action is always a map from your space cross z into your space. And if you take the quotient of this thing, you'll get the circle. Right? So this is the action. I will come back and define it more technologically correctly. And what you saw here is that these two things are large scale equivalent. And the theorem that we want to state today, and which there is a proof of, at least in the notes, I don't know if you'll get to there today in the class, is that there is a large scale equivalence between a group acting on certain kind of space and the group itself. So one has to define a notion of large scale geometry on a group. So how does one define large scale geometry on a group? So first let me just change this to say large scale geometry on a group. I know, my handwriting is beautiful. Just like when I put on a mask and get into U-Bahn, I'm the most handsome guy on the planet. So this is, so there is always a metric, there is often a metric on a group, but not on all groups. On certain kind of groups, you have an easy metric. Do you know a metric on a group? All right, so let's just define, you know, a group has generators, right? So a set F is called a generator. If what happens? If there is no proper subgroup, this is mathematical definition, there is no proper subgroup that contains F. Right? So a generator is, because every subset will generate a subgroup, and if that subgroup is not proper, what does it mean? It will generate the whole group. So this is just a weird mathematical sense of humor in defining what issue. People can also say, well, the set generates the whole group, right? But I deliberately did not want to define it like that, just to keep it more happy. And suppose the set is finite. So suppose F is finite. So this is an assumption. The group is called finitely generated, right? Okay, and that means that any element in the group, any gamma belong to, let me call my group gamma, is then gamma is gamma 1, gamma L, where gamma i's belong to F or gamma I inverse belong to F. So you can write down any element of the group as a word in the generators and their inverse. It's a word, right? And so the word length of a group, word length of gamma belonging to gamma is denoted by it depends on your generator, is the minimum of L gamma equals gamma 1 gamma N. Gamma I belong to F or gamma I inverse. So the smallest word that can be written in the generators, the smallest possible length is the word length. Okay? Make sense? And what this word length gives you immediately, more or less, without much effort, is a distance function, a metric. So once you have that, you can define d gamma 1 gamma 2 equals gamma 1 inverse gamma 2. So this is the word metric on gamma induced by. So note I have written induced by F. A group can have many different sets of generators. And every generator, how much time do we have actually? I've been very slow, I think, today.
We are halfway done.
Halfway done. Oh, I don't think we are halfway done in terms of the content posted on the lecture notes, but let's see. We don't have to rush, right? We are in no hurry to get anywhere. We are going to go far, far away. So this distance function, it's easy to check this is a distance function. I'm not going to check it. It's a baby homework. But if you are not convinced, check it. That this is a distance function. And this depends on a choice of generator. So if you want to say something about a group using this distance function, you will have to always remember the dependence on the generator, right? But there is good luck for us, at least in this world of large-scale geometry, is that it does not matter. In the large scale, now we have defined an equivalence between things. Or have we? We haven't. I forgot. See, this is the camera effect. I'm not going to ever say I'm growing old and forgetting things. I'm always going to blame it on the technology. Sometimes. So do you guys have to also teach? Some of you?
Yeah.
And do you like to teach without any notes in your hands?
Depending on the subject.
Yeah, I think sometimes you think you can teach everything without looking at any notes. But our memories are not perfect. So there is always an order of event in explaining stuff. And if you don't remember to say what comes first, at some other later point you feel, now what am I going to do about it?
But whenever I have notes, I get the feeling that, I don't know, that I stop thinking about what I'm teaching, and mostly that's not a good effect.
Yeah, actually, what's her name? Karin Ullenbeck, who got the last Abel Prize. I saw one of her lectures on YouTube, and she was saying that she never got used to giving lectures with notes, and now she's getting old, and she doesn't remember anything anymore. But this is a side effect. But I think this makes you a bit. You have to act on your feet, because if you forget something, you have to go back and fix it, right? But you're carried away. You're already somewhere else. So now I'm saying something about the group, and I define the word metric on a group. And what I would like to say is the following statement. So let me just say the statement. Maybe I'll call it a theorem. I don't know if I should legally call it a theorem. So if x df is word metric on a finitely generated group, gamma, oh, let me not say x, then I should call it gamma, with generator f, and let gamma d be any other. Now the words are quite okay. I think most of you understand this language. Translation invariant metric such that there are only finitely many elements in any bounded set. So one thing I know I have defined right now, right? I defined what it means to be a word metric with a set of generators. And now I'm saying, let there be any translation invariant metric on your group, with one caveat that it in any bounded set, in any certain set around where the distance doesn't blow up, there are only finitely many group elements. Just with that much caveat. I don't know anything about this other metric at all. But the claim is then the identity map induces a large scale or coarse equivalence between gamma df and gamma d. Sorry, why am I writing f when I'm trying to write gamma? I have no idea. Lost my brain. Okay, and now I realize what I have done incorrectly in terms of pedagogy. What did I not do? To state this theorem, I should have done something else before. There's also a lecture in teaching. What should I have done before? I should have defined what does it mean to be a large scale or coarse equivalence. Right? This is something I forgot to define. Okay, so what should we do now? Let's first think about what should it mean, and let's define it. So what we said is what are maps which are good for large scale geometry. I should really learn to write, man. Otherwise I'll just do too much exercise cleaning this board. And much of our time will be just lost in the board exercise. Okay, so what should you think is the coarse? What should you think is a coarse equivalence? So this is for the world people who like to think in terms of category. As soon as I define this phrase coarse equivalence, I have defined myself a category. As soon as I have defined this word, I have defined myself a coarse category, so to speak. With certain maps and at least certain spaces. Okay? So what should be a coarse equivalence? So let's define coarse equivalence. So actually there are various ways to define it, and I'm unfortunately stuck to one source for sake of consistency for our lecture course. What do they say? They say don't read. If you read the books that everyone else reads, then you think the thoughts that everyone else thinks. So one has to change different books to have different ideas of what one means by whatever. And different people can sometimes mean different things. But anyway, let's just stick with our worldview for now. So we defined, so if x and y are metric spaces, we define fx to y is a coarse map if it is monologous and inverse images or bounded sets are bounded. Right, so this is what we define to be a coarse map. So suppose we are given f(x) to y a coarse map, and g y to x is another coarse map. So when you have equivalence in the sense of in the world of category, there is one thing that should happen. What should happen is you should be able to go from one to the other. You should be able to come back. This is the only way to define equivalence. If you can only go one way, it's never an equivalence, right? So both of these, usually one would define, in most cases, one would define that FOG is the identity map on Y and GOF is identity map on X. But this is not what we want. This is not what we want. What we want is that FOG is equivalent to the identity map and GOF is equivalent to the identity map. And this is where our scales help us again. Right? So we say, let me define this. Oh, now I did not use my blackboard in a nice way. So def. So let X be a metric space. And as any set. Right? Then F1, F2 from S to X are close to each other. Close if there exists an R such that Fs, F1s, F2s belong to ERX for all S in X. What does that mean? So I have written it in terms of this language, our practice for a language, but can you elaborate it in your own mind? What does this mean? That for any element in the set, the distance between F1s and F2s is always less than or equal to R. So this is just a fancy way of saying that D F1s F2s is less than R for all s. The distance between the two images is less than s. Okay, so this is an equivalence. And when I say this is equivalent to that, I mean that FOG is close to identity, and Y and GOF is close to X. Okay. So if you are a category theorist, if you are interested in it, you can now check that with this equivalence and with this set of maps, we have defined a category of coarse spaces, of coarse metric spaces. But we don't have to do that, right? Not yet. I mean, unless someday we will use the homology theory on top of this. There is, by the way, homology theory on top of this. People have already developed it. So that's not what is going to make you rich and famous. You have to develop something else. Okay, so I think I removed the theorem that we wanted to prove. But that's all right. But at least we know what we want to prove. Actually, this theorem is the single most important piece of information that I want to know, other than the theorem that I talked about as the title of today's talk. This theorem says that no matter what word metric you choose, or whatever translation invariant metric you choose, the large scale structure is the same. There is a large scale equivalence created by just the identity map. Okay? And that is the main thing to remember. So I will say that. So I will restate that theorem that I erased in a different way. Is that there is a well-defined large scale or coarse structure on a finitely generated graph. Why do I say well-defined? Because the definition does not depend on the choice of, say, the generator. Right? This is what the theorem says. You define the metric space. You define the metric space using the generators, but the large scale quality of this metric space does not depend on the generator. So let me very, very shortly say something about the proof. What is it that makes something like that work? Right? So what have we assumed? So we want to say the identity map is a coarse map. So right. So we want to say if given r greater than 0. So if distance gamma 1, gamma 2 distance in the metric is less than r, what does that mean? It means that the word length of this thing with respect to this generator is less than r. So run with respect to this generator, it's hard. But what do we know? In any such set, how many gammas can there be? Because you have finitely many generator, how many gammas can satisfy this? Only finitely many. Right? So there was something that I'm. What is here? Okay, let's just. So there are only finitely many. Right. This is not the right proof actually. I all of a sudden realize. This is the proof in the other direction, but it's okay. Now I have told you a correct piece of information. This is not an incorrect piece of information. So the correct logic of proving this is that you can look at all the elements in the generator, right, and look at their distance with the other metric from the identity to gamma. This distance, you can take the max of this, or gamma belongs to the generator set, and its inverse, let's just say, or gamma I, inverse belongs to that. Max of this, you call this thing C. Okay? Then what do I want to know? I want to know how does the distance df and d relate for any x. So what I know that the metric is translation invariant. So if I look at this distance, this is equal to, so this is translation invariant, dx gamma. Okay, so this is translation invariance. So if I know x was made of gamma 1, gamma 2, gamma, whatever the length of this x, each time I can multiply by the inverse here, and I would get that so this is less than equal to, for every gamma I know the length is c, so I get c times distance, the length of x. Okay, I'm not being able to articulate this very well, but this is an induction argument. If your x was made of just one gamma, if it was just made of one gamma, then distance of this to the e would just be less than c by definition. We chose c to be that. Right? If it was made of two elements, right, then the distance of x to e would be less than c times 2 because of this translation invariance. Okay? So each step by induction, you add up one extra generator set, and you know that this length is less than equal to that. So it shows that the identity map in one direction, at least, is actually Lifshitz. Forget about more general thing. It is Lifshitz, and if it's Lifshitz, it's certainly going to be a monolarism. Right? And the other way around is an argument like this. You just count how many elements are in a set. But I'm going to leave it because maybe I can do it. How much time we have to? I also want to go somewhere. I mean, reach somewhere.
20 minutes.
Ah, that's a difficult decision now. Do we want to do proofs in detail, or do we want to reach somewhere?
Okay.
This is a philosophical decision.
Team proofs in detail. Team reach somewhere.
Oh, there are some people
I mean, it's 3 to 0, so I don't think it's representative.
I think I'm also going to vote for the proof is actually nicely written in the note. I know that proof is at least written nicely in the notes that I have uploaded. Okay, that's why I'm slightly reluctant to do it. The proof on the other side is what I have written here instead of df. It says that you count with the metric how many elements you have and take the maximum and blah and blah. This is a trickery that you will learn so many times that you will not even want to remember this. But the main purpose of the statement is this: you have a large scale. There is only one choice of large scale structure on a finitely generated group. It does not matter which generator set you take; they are all in the large scale the same. Okay. So now I want to talk a little bit about group actions. So how many of you are fine if I don't define what that means? Okay, good. Good, right? I think there is a definition in the notes anyhow, but I thought you should know what a group action means. There are certain special types of group actions. One kind of group actions are called co-compact. And the keyword is co. Right? And what would that mean? So I will always say gamma x on a metric space x, and I'm more or less always in this talk or in this course assumed by isometries for now. But this is not important for the definition, so this is just something to remember that we will often have it by isometries. That is what the point is, right? Group action means you are actually trying to find symmetries of something. You want to represent your group as the symmetries of this object. Right? So co-compact means there exists a compact set, K subset of X is compact such that union over gamma translates of, take this set, translate it with the group element, and take the union, and that should be all of X. So you can piece your whole X. What does this mean? That you have your X, and you can piece it. So K, gamma 1 times K, gamma 2 times K, gamma 3 times K. You can basically chop your space as bunch of compact pieces. So if you think of the quotient space, if you think about the quotient space might not be well defined. It may or may not be well defined. I think you know this kind of thing, when it is well defined and when it is not. But it should be thought of as being compact. So co-compact means the quotient should be thought of as compact. Okay, whenever the quotient is defined, it should be compact. The second interesting kind of group actions, so this is topologically interesting group actions, topologically important group actions. And the second interesting kind of group action is called proper. And I have no idea why mathematicians are so obsessed with this word, proper. There is proper this and proper that and proper here and proper there. And they are all different things, right? So we say gamma x properly on x if at each x and x there exists a neighborhood U, and now I will erase my beautiful drawing. Such that U intersection with the translate with gamma is not equal to an empty set. If U does intersect its own translate, then this can only happen only for finitely many gammas. That means usually this open set will be translated far away from itself and will not intersect itself. So this property says every point is thrown far away. Right? Not just the point, a neighborhood is thrown far away so that it does not intersect itself. The properness is trying to throw things far away. Okay? So these are two kind of balancing properties of group action. This is, you usually see if both of them are there, the world is very, very nice. It's not true that all group actions have both these properties. It's not true. That is why these are properties, not universal facts about group actions. But there is a very important class of examples. So again, since we do have people who do, has everybody studied a little bit of algebraic topology here? A little bit?
Yes.
Fundamental group? Covering space? Okay. So, what's the most basic example of a group acting with these two properties? What do you think? It takes all the examples that you learn in your covering space theory, every single last one of them.
The nicest example would be integers on R.
Integers on R. Right? Just this example. Why? Because is there a compact set whose translation will cover all of R? Right? So if you just take the closed interval 0, 1 and translate it with Z, then you get all of R. That's good. So this is certainly co-compact. Is this proper? Can at any point X, can I find a neighborhood whose translates don't intersect with itself, except for finitely many elements? What can I choose for a neighborhood?
A small interval.
Smaller than one interval, right? Because any translation of this, other than by the identity, other by the 0 in Z, will never intersect this interval. Okay? But this is not just unique to R and Z. As I was saying about your course in algebraic geometry, the example is basically X be the universal cover of a compact. For our case, I will just say manifold. Compact Hausdorff space is good. Well, I will say manifold. It's good. Doesn't matter. Right? Then compact manifold. So this has to have a name M. Right? Then pi 1, the fundamental group of M, acts properly and co-compactly. On X. Okay, so saying we want these two things, we should say, oh, our examples are not nothing, right? We should have some examples. So these are the examples that are the most interesting, most obvious examples, but you can come up with more. Is it good? Okay. With this, at least I'm ready to at least state the theorem that I'm interested in stating. I don't know how far we'll go with the proof of that, but if you're, so this is our example, and the theorem that is our goal is the Milnor Svarc. Actually, his name is often before because he proved the theorem independently and before Milnor. So that's why it's written the other way around. Let gamma act properly and co-compactly by isometries of a length space X. So this is our assumption, right? So all these examples here automatically, see if you choose any Riemannian metric on M, if M is a closed manifold, you can pull back its metric on the universal cover, and that will be an isometric action of the fundamental. Okay, so gamma is something that acts properly, compactly on a length space X. Then gamma is coarsely equivalent to X. Period. That's it. Okay? Now you say, okay, man, this just is a generalization of example like that. Why do you really care, right? This is like somebody trying to be wise, generalize, trying to imitate Grothendieck. Why would you care? But you would care if I say some more stuff. So now I have said this gamma is coarsely equivalent to X. So I'm just first going to talk about the implications of this theorem for a bit, and I think the proof will have to either be postponed to the next lecture or we'll see what to do. So in the first lecture, what did we prove about the hyperbolic space? In the first lecture, we proved that the hyperbolic space Hm, last time, we proved that the hyperbolic space is Gromov hyperbolic. Although I don't think I used the word like that. Or did I? I don't think I did. No. Which means basically the triangle property. That there exists a delta, a priori given delta greater than 0, such that for any geodesic triangle, AB is in delta neighborhood of AC union. So this is the property, right? In the next lecture, or maybe it will take more than one lecture to finish the proof or talk about it in completeness, but what I want to say that this Gromov hyperbolicity is a coarse property. So if you have two geodesic metric spaces which are coarsely equivalent, one of them is Gromov hyperbolic, and the other is also Gromov hyperbolic. Okay, so I will state it again. Don't worry. Now, what do we have said? We have proved that this is Gromov hyperbolic. We know that any group that acts on the hyperbolic space properly and co-compactly should also be Gromov hyperbolic. Can you tell me a few examples of groups that act on the hyperbolic space? Just from this, from the fundamental group examples.
The fundamental group of negative Euler characteristic smooth surfaces.
Exactly. So if you have S is any closed surface with G greater than or equal to 2, with G is greater than 2, then what one knows is that the universal cover of H is the hyperbolic space plane, and this will imply that the fundamental group of S is so although you might think of this Milnor-Schwarz theorem as not that big a deal, but you can see that it immediately proves results that you are interested in proving. Of course, it requires you to also prove this in between statement. So that statement and this statement, Gromov hyperbolicity is a large scale invariant. If you prove that, so that plus this will imply that. Agreed? And this is the kind of mathematics we are interested in this course. Okay? So we have proved something about the groups, about the class of groups, by doing metric geometry and studying the hyperbolic space.
I'm just wondering, so this, I hope I'm not interrupting you at a crucial
Sure.
point.
No.
Okay, but
I think we're already out of time, no?
Yeah, so the group metric with respect to some generator, can you translate that in terms of edge metric on the Cayley graph? Is that correct?
Yeah. So actually, the word metric is what I introduced. What I should also have introduced, certainly written in the notes, is that what you can do is you can create the Cayley graph, as you say, with the same generators. And the Cayley graph, the metric on the Cayley graph has some advantage of the metric over the group. And the advantage is that the Cayley graph is a length space. And the group sitting in the Cayley graph as vertices of the Cayley graph is an isometric embedding. So whenever I'm writing theorems where X has to be a length space or something like that. And if your group is not being a length space itself as a word metric, which is not going to be the case, you replace it with a Cayley graph and you can still get all the results applicable to it. So the advantage of using a Cayley graph, which is at first feels like an artificial construction, is that it makes the group essentially look like a length space. But yeah, I should have mentioned that it's also part of this very discussion. Right?
For example, our main leading example with R in the integers is just when I take the Cayley graph of the integers with the generator 1, right?
Hey, then you get R, right?
Yeah.
Yeah, that is another way of looking at R.
And possibly could topologically define the interval and the integers via some basic axioms and never define the reals.
If you want to do that.
No, I don't.
Now, I mean, the thing is how typically you'd learn it is like you define Z from the Zermelo-Frankel exons, and that's it. I mean, Once you have defined Z, everything else follows. Or and, actually there's another Frankel exam, only define you the Z and plus. It's 0, 1, 2, 3. So actual numbers.
One more question. I did not notice. How is the fundamental cover of genus greater than 2 service hyperbolic space? Like, what does the matter come from?
Yeah, so this is basically saying that any of these things can be written as you can draw a certain polyhedron polygon in the hyperbolic space and identify the opposite edges. So you can say that you cannot actually put a rectangle in the hyperbolic space. You cannot embed a rectangle with all 4 sides being geodesics in the hyperbolic geometry. But if you allow more edges, then those higher edges polygons can be embedded into hyperbolic space. And so when you restrict the hyperbolic metric to this, include the ends, you get a -1 metric on the hyperbolic on any genus 2 greater than 2 surface. Right? So if you have a -1 space surface, Hadamard's theorem already tells you that its universal cover is diffeomorphic to Rn with constant -1 metric. What else can it be?
Yeah.
So that's one way to think about it. There are many ways to think about it actually. That's the first.
I mean, yeah, what you said, of course. Yeah, okay. Already assumes, of course, that you have this hyperbolic metric on the genus. I don't know. Quite equal to
Yeah. And that automatically means that your group action as the group action of the fundamental group on the universal curve with that metric is isometric. Because that's one of the assumptions in this theorem. In the Milnor's Svarc theorem is that the group should act by isometries. Right? So, which will be the case. Okay. So yeah, there is some, but we will talk about these things maybe in more detail. But I wanted to advertise where we are going. I will do some part of the proof of this theorem. The proof is really not that instructive, to be really honest. It's the same proof as for R and Z. Absolutely the same proof. No big deal. Right? So I don't know how much time I want to spend on that. It's the same proof. But of course I want to spend a lot of time on this. That the Gromov hyperbolicity is a coarse property. Okay. So that is one direction of going it, and we will also do more topological stuff. In what order actually people prefer group theory? How many people would like more group theory? None of you.
I'm not against.
I mean, it depends on what exactly we're gonna do.
Well, certainly one should know a little bit about amenability.
That would be interesting.
Yeah. The thing is that till you know amenable and non-amenable groups, all groups look the same. And once you learn these two words and understand them, you think some groups are easy and some groups are horrible. That is the point when it hits you. But it's good to come to that point. I think it's good to know this reality about groups.
I've had a similar feeling with abelian and non-abelian.
Yeah, but non-abelian is life, right? I mean,
Yeah, it's a matter of choice.
you cannot permute n objects in abelian manner. I mean, I'm sorry, and there are more than n objects in this universe, and greater than 2 objects in this universe. And sometimes you end
That's a philosophical statement.
Yeah.
I believe there's only one of them.
Well, that is indeed a philosophy. Okay. Technical expertise.
has to put in also
Very good thought as well. Click here, yes.
I have to click there. Here.
More was is